Transportation engineers tend to talk about the interstate construction days with just a touch of nostalgia, and with good reason. There were some huge construction projects, work that called on the very best engineering talents available. The challenges were tremendous. Roadways, ramps, bridges, drainage structures, all in one integrated system. The scale of the interstate network is truly awesome. In comparison, you tend to think of today's projects, largely reconstruction and rehabilitation, as being far less challenging. Right, except for that one little variation: traffic. The interstate system was constructed on new right-of-way, and most of it was done with no interference from traffic. No wonder there's nostalgia in the air. Virtually all of today's highway work is done adjacent to or in the middle of traffic, and high-speed traffic at that. Today's construction or maintenance worker spends the whole day trespassing on the driver's territory, and that driver doesn't want to give up 1 inch of the roadway. Doesn't want to slow down either. Getting that driver through a work zone safely is a challenge that matches a lot of those that we faced in the interstate days. Fortunately, as a result of research and development over the past decades, we have some impressive tools to work with: standard signs, cones, drums, barricades, and the rest. If they're applied with good, solid engineering judgment, following the standards in the MUTCD, the margin of safety is greatly enhanced. This program focuses on just one traffic control device, and it's a powerful one: the Advance Warning Arrow Panel, commonly called Flashing Arrow Panel. Advance Warning Arrow Panels are sign panels with a matrix of lights capable of either flashing or sequential displays. In places where the driver's attention might be divided a dozen ways, the Advance Warning or Flashing Arrow Panel is riveting. The driver's eye goes straight to it, and the message is clear. Even at night or in bad weather, when visibility, perhaps more than any other factor, determines whether the driver is going to make it to the other end of the work zone. The arrow panel's single outstanding message is lane closed ahead. It can be a one-lane closure on the right, the left, or in the center of a multi-lane roadway. Panels can also lead drivers through multiple lane closures, left, right, or center. Lanes are frequently closed by slow-moving maintenance operations, such as this striping crew. Arrow panels mounted on each vehicle in the convoy force drivers to pay close attention to the potential hazard ahead. And shoulder closures often call for advance warning as well, operating the arrow panel in its caution mode. Although the arrow panel is a highly useful device that carries a strong message and provides good guidance, it's not intended to be used alone. It's almost always used to supplement other devices. This program does not deal with all the other devices in the work area. For more information, refer to the Federal Highway Administration's Manual on Uniform Traffic Control Devices, the MUTCD, and your own agency's references. The federal MUTCD has explicit minimum standards for arrow panels. All state traffic control manuals must either conform with the MUTCD standards or exceed them. This program is designed to help out. It covers the mode selections, design standards, applications and placement standards, costs and equipment maintenance, and some general recommendations for operation and usage. First, of course, the mode selections. Arrow panels should have the capability of the following operating modes or displays: left flashing arrow, right flashing arrow, left sequential arrow, right sequential arrow, left sequential chevron, right sequential chevron, double flashing arrows, and caution. The caution mode consists of 4 or more lamps arranged in a pattern that does not indicate a direction. That's usually either 4 lamps in the corners or the arrow shaft alone. Now, many engineers prefer not to use just the arrow shaft, though, believing that drivers may interpret it as a malfunctioning arrow and may change lanes unnecessarily. If you have any doubt, use the 4-corner mode. To move traffic to the left or to the right, drivers appear to get the message most clearly through the flashing arrow and the sequential chevron. Those are the preferred displays for left and right side lane closures. So those are the standard mode selections: sequential or flashing arrows, sequential chevrons, double arrows, and the caution mode. Which brings us to the design standards. All arrow panels that conform to the MUTCD's requirements are rectangular with yellow lamps and a flat black finish for good contrast. To reduce glare from sunlight, the lamps have to be either recessed into the panel or equipped with hoods that cover at least 180 degrees. This design makes the display highly visible, even in bright sunlight or with distractions in the background. There are 3 sizes corresponding with 3 levels of traffic volumes and speeds. Type A panels measure 24 inches by 48 inches. They have at least 12 lamps and must be legible from a distance of 1/2 mile. They're appropriate for low-speed urban streets. Type B panels are 30 by 60 with at least 13 lamps, and they have to be legible from 3/4 of a mile. They're designed for intermediate speed and for maintenance or moving operations on high-speed roadways. And Type C panels are 48 by 96 with at least 15 lamps, legible from a full mile. Type C is designed for high-speed, high-volume roadways. All of these numbers are in the MUTCD, of course, along with the other requirements. There's no need to try to remember all the specifics. The minimum lamp on time is 50% for flashing arrows and 25% for sequential chevrons. Those minimums give you the best recognition factor. Both types of arrow panels must be capable of at least 50% dimming from their rated lamp voltage. The panel in this footage is being operated at full power, and as you can see, it's overpowering. As you get closer, it can almost blind you. Clearly, that doesn't add to driver safety. In contrast, here's a panel being operated at 50% of its rated voltage. Good recognition, high visibility, and no blinding glare. So the reasoning behind the dimming requirement is obvious. Although some panels have manual dimming controls, clearly it's best to have the dimmer operated by a photocell. Photocell systems operate automatically, sensing the ambient light and dimming the lamps appropriately. That way, no one can forget to turn down the brightness at the end of the day. Now, mounting height. The minimum height for all arrow panels is 7 feet, measured from the edge of the roadway to the bottom of the panel. Now, the reasoning here is obvious as well. Maximum visibility, even over vehicles driving ahead of you. There's one exception to the 7-foot minimum mounting height. It's not always possible to get the panel mounted 7 feet up on the back of a work vehicle. For maximum visibility and maximum safety, though, it should be as high as possible. As you'd imagine, the alignment of the panel head, both vertical and horizontal, has a direct effect on visibility. After all, if you can't see it, you can't respond to it. The horizontal alignment is controlled by positioning the trailer, and the vertical alignment is controlled at the panel mount. The goal, of course, is to make the panel visible from as far away as possible and to keep it visible as drivers approach the work area. Because of the panel's high-intensity lights, this isn't a precision alignment, but the operator should always be trying for maximum effectiveness. The power supplies of aero panels include diesel, gasoline, solar, and batteries. While the MUTCD does not contain any standards for power supplies, some state transportation agencies require self-contained power supplies that are capable of running aero panels for at least 72 hours. Diesel generators are the most commonly used power supply, and while some gasoline-powered generators are still operated, their use should be avoided whenever possible. Because aero panels are often exposed to traffic, collisions are possible, and, in an accident, diesel fuel presents a lesser fire hazard than gasoline. The use of solar-powered aero panels is becoming more widespread. Solar collectors mounted on the trailer charge batteries that power the lamps. The collection panel should be positioned to catch the maximum amount of sunlight. And there should be enough batteries to power the lamps during periods when little sunlight can be collected. Fully charged batteries can run a panel for weeks, depending on ambient temperature. Other aero panels are powered by batteries alone. As the batteries are used up, they are rotated with recharged ones to maintain a steady power supply. Of course, vehicle-mounted panels don't require their own power supply. They're designed to run off the vehicle's battery system. Okay, so those are the design standards. Now, applications and placement. Situations best suited to the use of an aero panel and where to place it for best results. As I mentioned earlier, the aero panel's overriding message to drivers is lane closed ahead. Research has shown that drivers start preparing to merge as soon as they see an aero panel. Lane closures, then, are the single most suitable application. But not to close one lane of a two-lane, two-way road. Clearly, if you close one lane of a two-way road by using a flashing arrow, drivers could be guided into the path of oncoming traffic. Aero panels are primarily suited for use on multiple lane roadways. When an aero panel is used in conjunction with channelizing devices, it's always best to install the panel off the roadway at the beginning of the taper, on the shoulder if possible. Now, granted, the panel isn't directly in line with the driver's eye, but the message is still clear. And you have to remember that the panel itself is a potential collision hazard, so it's best to keep it out of the way. For a single lane closure, a transition taper of length L is formed with channelizing devices. L is determined by using one of two formulas given in the MUTCD. This is followed by a buffer space of sufficient length to give the driver one last opportunity to bring his vehicle to a stop before entering the work area itself. The buffer space and the work area are outlined with a series of channelizing devices. And finally, the aero panel is placed in its standard position at the beginning of the transition taper. In a multiple lane closure, most transportation agencies run the standard taper length L to close one lane, then a tangent section of 2L to allow traffic to stabilize, then another taper L to close the next lane, and a tangent section running past the work area. An aero panel is placed on the shoulder at the beginning of the first taper, and a second panel is placed in the lane that was closed first, at the beginning of the second taper. For the center lane work area shown here, first, the left lane of the roadway is closed. An aero panel is placed on the shoulder at the beginning of the lane closure taper. A standard taper length is set up, followed by a tangent section of 1/2 L. Then, the traffic is divided, allowing the right lane of traffic to pass to the right of the work area, and the left lane of traffic to pass to the left of the work area. The center lane is closed with channelizing devices as shown. An optional panel displaying a double arrow can be placed toward the back of the taper. That way, the trailer fits well between the rows of channelizing devices, and the panel itself doesn't encroach on the travel lanes. Frequently, space is simply too limited to put the panel off to the side of the closed lane where it should be. Here, for example, moving the panel to the right would place it on the sidewalk among the trees. So as the next best placement, it's been positioned as close as possible to the beginning of the taper, behind the channelizing devices. Placement at the start of the taper is always preferred over placement in the middle of the taper. So that's the general rule, either on the shoulder at the beginning of the taper or behind the channelizing devices, as close as possible to the beginning of the taper. But the real world isn't so neatly defined as that. No two work sites are identical, and the overriding rule is visibility. If drivers won't have enough time to see the panel and react to its message, make adjustments. Here's a quote from the MUTCD. Placement of the aero panel should be varied as needed to achieve recognition distances. So if hills, curves, or other obstructions reduce that desired recognition distance, the panel can be moved upstream by as much as 2,500 feet. If the panel must be moved upstream, try to locate it on the shoulder, not in a traveled lane. If there's no space on the shoulder at that point, you should probably consider bringing the taper upstream as well and extending the lane closure. Another problem to watch for is the potential for confusion with nearby ramps, median crossovers, and intersections. Take a close look at all the possibilities. How will drivers react to any single placement? Are you giving them the positive guidance they really need? Would a minor adjustment produce the effect you want? Lanes are frequently closed by mobile construction or maintenance operations, pavement recycling, patching, and so on. The aero panel, mounted on a vehicle at the back of the operation, uses the same panel displays as would be used for a stationary operation. A flashing right arrow for left lane closures, a flashing left arrow for right lane closures, and a double arrow for center lane closures. When aero panels are used for shoulder closures, they should be operated in the caution mode, not as a flashing arrow. The flashing arrow tells the driver to move over, and shoulder closures don't call for a reaction, just for heightened attention. So, those are the major applications and placement standards for single lane closures, multiple lane closures, center lane work areas, and shoulder closures. Now, some agencies use aero panels for another application, traffic diversions or shifts. But since an aero panel is mostly understood as indicating a lane closure, it should be used in a lane shift situation only after an engineering study justifies its use. Now, costs and maintenance. As you'd expect with a fairly complex piece of equipment, aero panels don't come cheap. Truck-mounted panels, depending on their size, cost something like $750 to $2,000. And you have to remember, they run off the truck's generator, so they don't have a special power supply. Trailer-mounted aero panels with generators cost about $5,000. Most engineers tend to agree that given the increased effectiveness in terms of traffic control and traffic safety, $5,000 is a bargain. But bargain or no bargain, $5,000 is an investment, and that investment has to be protected through regular, scheduled maintenance. Like any other traffic control device, especially in work zones, aero panels need attention periodically. Of course, all engines need oil changes and so on, and the generator for an aero panel is no different. But in this program, we're concerned only with the maintenance work that affects the operating effectiveness of the aero itself. That is, maintenance that affects traffic safety. First, naturally, that means the lamps and lenses. The traffic control supervisor should frequently check the display to see that all lamps are lit. Replacing lamps may appear to be an unproductive chore, but an incomplete aero is an incomplete message to the driver. Given the time and cost invested in installing an aero panel, there's just no reason to settle for less than 100% effectiveness. Road grime is a concern in all work areas, and depending on the road conditions, the aero panel's effectiveness can be reduced by 50% or more in a short period of time. Lenses should be cleaned on a regular schedule, and the cleaning should be more frequent if road conditions indicate a reduction in visibility. As I mentioned earlier, many aero panels are equipped with photocells to automatically dim the lamps at night. You have to remember that photocells aren't fail-safe. They should be checked on the same schedule as the other maintenance items. If the sensing element is caked with road grime, the dimming can be actuated during daylight hours. And of course, if it's defective, it should be repaired or replaced. The amount of dimming required can vary a good deal from one location to the next. As you'd imagine, the ambient light in a brightly lit urban area is quite different from the light on a remote rural highway. The best test is a nighttime drive through the work zone. The first night the panel is installed, with adjustments made on the spot. The flashing frequency rarely needs adjustment. Just check now and then to see that the display runs at 25 to 40 flashes per minute. For most projects, one person should be in charge of maintaining the aero panels. On panels that have their own generators, very little is likely to go wrong between refuelings. But every time the tank is filled, the operator should give the whole unit a good look. Lamps, lenses, dimming controls, and so on. Panels without generators should be checked at least every few days. Same items. And in any case, all project personnel should be encouraged to watch for problems and report them as soon as possible. Like all other traffic control devices, an aero panel can be highly effective or practically worthless. Well, now that we've covered mode selections, design standards, applications and placement standards, and costs and maintenance, here are the key recommendations. First, make sure that all MUTCD standards are satisfied as a minimum. Then refer to your own agency standards. Don't use aero panels to close lanes on two-lane, two-way roadways. The potential for misguiding traffic is just too great. Whenever it's possible, place aero panels on the shoulder at the beginning of the taper. If there's no shoulder or not enough space off the roadway, place the aero panel as close as possible to the beginning of the taper, behind the channelizing devices. Where sight distance is limited, consider using a supplemental aero in advance of the work zone, or extend the lane closure upstream to a point where visibility is acceptable. If multiple panels are being installed, the spacing between them should be at least 3 times the taper length L found in the MUTCD, and never less than 1,000 feet. Closer spacings tend to overpower drivers, and they can react erratically. If a double aero seems warranted, watch the traffic movements immediately after installation. If it causes confusion, make adjustments, or remove it. And finally, enforce all requirements for dimming the lamps at night. Drivers who are blinded as they pass an aero panel simply can't be expected to react safely. Aero panels are relatively new traffic control devices. The research and development efforts are far from complete. Given our relatively short experience with them, we basically know just 2 things. In the right situation, the expense really is a bargain. And in the wrong situation, or if they're not placed and operated with care, they can cause more problems than they solve. The flashing aero panel. It's a powerful device, not to be taken lightly.